So welcome. So here we are, and we're going to do our second part of this content, which is basically talking about the the vectors. We've done the two-dimensional motion by combining everything on the x-axis and then combining everything on the y-axis. So we have the component of our answer along x, we have the component of our answer along y. And then if we want to find the answer, what's the final speed? We can combine these components and we can get the speed and the direction. Or what's our final displacement? We can combine these displacements to get the final position. So that's the kind of name of the game we play, and this keeps coming up. And this principle about dividing things into x's and dividing things into y's and keeping two columns and then comparing, we'll use over and over again. However, it raises the point about, is there a way that we could actually do this using IJK nomenclature? IJK is really powerful for 3 dimensions. Personally, I didn't see the value of it for 2 dimensions, but I realized when we went to 3 dimensions that it's a really useful thing. It's a great way of bookkeeping, just keeping track of where things are. So we're going to look at that now. So, yeah, we've learned that in components, whether it's the x-axis or the y-axis, we can just use good old kinematic equations. So Vf equals Vi plus A delta t, and delta x equals a half Vi plus Vf bracket delta t, and delta x equals Vi delta t plus 1/2 A delta t squared, and Vf squared equals Vi squared plus 2A delta x. We know these, but the trick is we only do x stuff with x stuff, and we only do y stuff with y stuff. And so now I'm saying, well, why can't we do IJK stuff with IJK stuff? So why can't we just say vector Vf is equal to vector Vi plus vector acceleration times the time interval? Why doesn't that work? And actually we find it does. So these are great, that's great, and that's great, and that's great, but I don't have much of a clue about that because I don't know how to multiply 2 IJKs together as yet. So what we find is that this works a lot of the time, but not all the time. So we still want you to know components. It's just there are times when this is really, really helpful. So my advice is that you really make sure you got components down, because that's going to really matter. And don't regard this as replacing components, regard this as adding to components, and you'll see. The IJK is a way of doing shorthand, and it sometimes saves you a lot of work. So this is kind of what we're at. I could have, and I'm showing this in 2 dimensions rather than 3, which kind of like, in a way, spoils it a bit. But what I'm saying is that the vector answer, which is Vf, is equal to the vector addition of Vi plus A times delta t. Should be delta t. That I could draw a 3-dimensional diagram that would show this. And graphically, they call it delta r rather than delta x. It's just tradition. If you put down delta x, it doesn't matter. But delta r equals Vi delta t plus 1/2 A delta t squared. And there's your answer. So I can look at this thing graphically. I can look at it in components, and I can do it as an IJK. So that's the game I'm going to play. Particle has an initial velocity. I'm not going to draw this to scale. I'm just going to say it's got an initial velocity, and that's my Vi. And it has an acceleration. I don't know what this acceleration is. Let's just put it down like that. Acceleration of that. What is its vector velocity after 6 seconds? Well, I do know some things. I know that velocity is going to tend to be curved around by that acceleration. So I can guess that my path is going to be something like that. And at the end of my path, my V final is going to be something like that. And this is t equals 0 seconds, and this is t equals 6 seconds. Now, you don't need to be able to do that to be able to solve this problem. But the more you can do stuff like that, the more the problems become just like, I can visualize this is fine. And my advice is you really do try and, you're not satisfied with, yeah, I can recognize the variable and plug in the numbers. But you recognize, oh, I can see that in my head. And I can figure out what's going on. That, I think, really helps. That means you go to the next level of being powerful. So there's my visualization. And then I want a list. So I'm going to say, well, my VI equals, and it's going to be 3I minus, not plus, minus 2J plus 4K. And that's the velocity, so that's going to be in meters per second. And then I guess I have a acceleration, and my acceleration is equal to minus 2I plus 4J minus 6K. And that's going to be in meters per second squared. And then my time interval, it says after 6 seconds. So I know my time interval is 6 seconds. Remember, I'm always trying to make it so that you can't just look at an equation and plug the only numbers I give you in. So it's very tempting for me not to say after 6 seconds, but to say at time t equals 3 seconds, that's your velocity. And then there's a constant acceleration, and then what's your velocity at t equals 9 seconds? So I took you from 3 to 9, which is still 6. It's asking the same question, just in a different way. Mathematically, it's the same. But then I'll find some people will put down 9 seconds for the time, because, again, they're just looking for a number to plug into an equation. So try and put yourself in my shoes. What would you do to make sure that students are really trying to visualize as opposed to just plugging numbers in? And then the thing you want next is I want to know my V final. So I think and I think and I think, and I go, oh yeah, I know this one. Vf is equal to Vi plus A delta t. Now, you know, really that's a vector, and that's a vector, and that's a vector, but that's not. So I could put my vectors here. I used to not worry about this, and so I got sloppy about what was a scalar and what was a vector. And it's when I tightened up a bit and said, that's a vector, put an arrow on top of it, that's a scalar, leave it alone, that thing got clearer for me. So attention to detail is sometimes really helpful. I want to find VF, so I just need a layout now. So I like to have the layout as a grid. It just means that there's not numbers floating around. I hate numbers to be floating around. And then I say, well, okay, the first thing I want is VI, so let's just write down VI. So I look at my list and I go, well, that's 3, and that's minus 2, and that's plus 4. And then the next thing I want is A delta t. A delta t. And, you know, delta t 6. I can multiply this by 6. So that goes to minus 2 times 6 is minus 12. And then plus 4 times 6 is plus 24. And then minus 6 times 6 is minus 36. I don't like to do things in my head, but I can do that in my head. That's not that big a deal. And then that operator there tells me to add. So I add these guys together, and I'm going to go, oh, that's going to be minus 9. And that's going to be plus 22, and this is going to be minus 32. So my answer is minus 9i plus 22j minus 32k. And that's a velocity, so that's meters per second. Don't want to forget my units. And then I put it in a box so that I can find it. And that's it. That's like, now let's think about what we just did. I had a vector in some wacky direction, which was my initial velocity. I had a vector in some other wacky direction that was my acceleration. And then using one equation, an IJK symbolism, I was able to work out a 3-dimensional vector sometime later. That's really powerful. And it seems mathematically easy. And the reason is because of the layout. It's kind of like, you're not kind of holding things in your head, and you're not going, use only the x-axis and use only the y-axis, and use, you know, I give you it in components if you think about it. I'm giving you it in components, and you're kind of like just keeping your columns of components nice. In a way, it's cheating a bit. There's no angles in here. I've already broken it up to the components, so I'm kind of making the problem a bit more straightforward. Cool. If I want to do, in this problem, I kind of told you everything, didn't I? I told you VI, I told you A, I told you delta T, and I asked you for VF. I could have put something in like the temperature, just so that I give you another number to worry about. It's got nothing to do with the problem. That's fair game. But people pretty soon recognize that. But there's other things I can do where all I have to do is say this is a projectile. And now I've told you a whole bunch of information just by that one word. If it's a projectile, there's no air resistance, but there is an acceleration. You already know the acceleration because it's a projectile. And can you write down for me, please? Just commit to it now. Just write down, what is the vector acceleration? What would you write down if I said, I want you to give me the ijk vector for the acceleration during this journey? Just decide, what would you write down? And then I want you to turn around to the person next to you and just compare notes and see if you agree with each other. Okay? IJK. What's the IJK? What would you write down for the IJK vector? And, you know, the first one, does it have any x component? Is there any component of acceleration horizontally? The answer is no, so that's 0I. Is there a y component, a vertical component? Yeah, minus 10j. And then is there a out of the page component? Nah, 0k. Meters per second squared. So I told you that without, just by saying projectile, I told you that, okay? Projectile has an initial velocity of that. So again, don't worry about drawing it to scale, just draw it. So there's my initial velocity. What is its vector displacement after 3 seconds? That's it. I mean, that leaves, there's like next to nothing said. A projectile. Oh yeah. I'm going to change colors because it's, I wish I could, I can actually in this system, I can. The two computers in the two different rooms have, no I can't. Rats. I thought I could on this. Oh well. The two computers in the two different rooms have two different programs on them for some reason, which is a bit annoying. So there's my A. Now, what I know is throughout the journey that A is going to be applied. It's constant A. So I can pretty well predict that this is going to go boom, something like that. That acceleration is going to win out in the end. Why is it going to win out in the end? Because throughout the journey, you know, throughout the journey, that A is constant and it keeps dragging it in that direction. You know, we don't need to draw all that, but that's kind of what's going on. And so by the end of my journey, let's go back to red. By the end of the journey, I'm here, there's my VF, but I don't want VF this time. I want displacement. So here I am when t equaled 0 seconds, I was way over here. And when t equals 3 seconds, I'm there. But I want to know that. I want to know that delta R. So I make my list. And I say VI is equal to, I'm looking at the words, plus 5I minus 4J plus 6K meters per second. And then let's have a look. A is going to equal 0I minus 10J plus 0K meters per second squared. And my delta t, and again I gave you the delta t this time, I said after 3 seconds, that's a big giveaway for the delta t. And so I want to find my displacement. dr, delta r we call it, you know, it's delta x would be just as good. And delta r equals, I don't know, but I do know that delta r is equal to vi delta t plus 1/2 a delta t squared. And the vi is a vector, and that's a vector. Oh, it's just a sum at this point, so I go I, j, k. Again, it's just bookkeeping now. And I know my first term is vi delta t. So my delta t is 3, and my vi is up here. I can multiply these guys out. 3 times 5 is 15. And then 3 times minus 4 is minus 12. And then 3 times 6 is 18. That's that first step done. And then I want to add on this second step. And the second step, you know, it's a little bit more challenging to do in my head, but I think I can do it. 1/2 times a times delta t squared. Well, let's have a look. Delta t is 3, so 3 3s are 9, and 1/2 and 9 is 4.5. So I've got to multiply a by 4.5, but a is very simple. So that's going to be 0, because 4.5 times 0 is 0, and 4.5 times minus 10 is minus 45, and 4.5 times 0 is 0. So it's not as bad as you might have thought it would be. And then that gives me together, that gives me delta r. So this is, and this is operators and addition, so I just add, and I say plus 15 minus 57 and plus 18. So I'd say my delta r is equal to plus 15i minus 57j plus 18k. And that's going to be in meters. And there we have it. So not bad, is it? It's like not bad. You just did a 3-dimensional thing. It worked. Can you see? So this is my little pitch to you. Can you see how just, to my mind, when I look at that diagram and it's in colours, it's much more clear than if it's just in one pen. I mean, you get used to it, and you know. But you know, if you're finding that your diagrams need a bit of work, I would strongly suggest you get one of those 4-colour kind of like biro pens that you get at Staples. You know, 4 little clicks on there, and just put your accelerations in one colour and your velocities in other colours, so you don't get the two of them confused. They're not just all arrows. There's red arrows and purple arrows and green arrows, and you're kind of codifying, saying they mean different things. You know, it does help. And then eventually you can just let go and just use pencil, and you're fine. But, you know. I'm going to draw a bit of a line now. This is, so we've done kinematics in 2 dimensions, and we've done them in 3 dimensions. And now we're doing another thing that's in 2 dimensions, but it's not using kinematics. So it's called relative motion. I don't know if you ever had it, but I remember when I was a kid in school, they'd give me these questions. We call them intelligence tests, which I have no idea. I don't have much faith in those things. Aptitude tests. There is a little bit of a cultural difference in that. I think in my cultural background, my school did not care what your aptitude was. They cared, could you do it? You know, could you do it? So they worked us really hard to make up. If we didn't have the aptitude, they just worked us really hard. We had tons of homework. That was what my school did. And I found with my daughter, it's just a lot of aptitude tests. And it's like, well, yeah, she might be bright, but, you know, is she acquiring skills? It's kind of a bit different. It's not. But one of the questions I remember from my own aptitude test was, you know, Michael gets on the bus and runs to the front of the bus, because you get on at the back in Britain, runs to the front of the bus while the bus reverses, you know. He runs to the front at 10 feet per second, and he reverses at 7 feet per second. And what is Michael's speed relative to his uncle, you know? It's like you kind of, well, it's going that way, and it's going that way, and it's... And you always get them. It's one of those things where you know it's either added to or subtracted, and it's a 50-50 shot whether you get it right or wrong. Well, this is in 3 dimensions, so man, this is gonna get the whole heart pumping. But this is one of those examples where, you know, everything here is designed to make you stronger, and the fact of the matter is that, you know, they make hard problems easier by using technique. So here's the technique. I have, you know, 3 objects that are measuring their speed relative to each other. The nomenclature's, you know, it's basically, well, this is the velocity of B as measured by A, and this is the velocity of C as measured by A, and this is the velocity of C as measured by B, you know. And looking back to our vector diagrams, I'm going to give you 3 choices. Vector AC is equal to vector AB plus vector BC, or vector AB is vector AC plus vector BC, or vector AC is equal to vector AB plus vector. Is that the same thing I'm doing again? Yeah. Vector CB. I'm making 3 things up. Those are not all right. One of them's right. And in diagrams, what's the process of addition? How can you tell when 2 vectors have been added together? What do you look at on the diagram and you go, oh yeah, those 2 got added together because, and what is it?
Arrowheads.
Pardon? The arrowheads. The tail of the first arrowhead is supporting, the head of the first arrowhead is supporting the tail of the second arrowhead. You put things end to end, yeah? That's addition. So those 2 have been added, but those 2 have not, tail to tail, and those 2 have not, head to head. So I can look at this and I can say, oh yeah, AC is equal to AB added to BC. That's the one that's right. The other 2 are wrong. And then if I generalize that, what I see is, oh, I get it. We started with A in both cases. We started here in both cases. We ended at C in both cases. We ended at C in both cases. And for the long one, the addition, B was stuck in the middle. B was stuck in the middle. So there's a certain kind of like pattern to it, you know. So now I want to say the velocity of the spaceship relative to the moon is equal to the velocity of the spaceship relative to Jupiter plus the velocity of Jupiter relative to the moon. And I know that because we start with the spaceship and we end with the moon, and Jupiter's the thing that links the 2 of them. Simple as that. So John has a velocity of that relative to Bill. So V, John, relative to the Bill, is equal to 3I plus 2J plus 4K meters per second. And then we have Lisa has a velocity. V Lisa has a velocity relative to the bill of minus 2I minus 3J plus 4K meters per second. What is the velocity of Lisa, the Lisa, relative to John? Now you've got to get used to putting your letters down in the same order. You know, you got to know, oh yeah, it's John, Bill, that's JB, and it's Lisa, Bill, that's LB, and they want Lisa, John, that's LJ. You've got to use the same terminology each time. You can't suddenly decide to reverse the order of your letters. You've got to do it. And I'm not going to try and trick you like that. I'm just going to give you some instructions. So then you say, okay, well, the velocity of Lisa relative to John equals, and I'm just making up my equation. I know I've got to start with Lisa, and I know I've got to end with John, and I'm going to add these two guys together, and then I know the intermediary is Bill. So that was pretty straightforward. I need a grid, so IJK. Now, velocity of Lisa relative to Bill. I've got that one. They gave me that one. That's great. So let's put that down. That's going to be minus 2 minus 3 plus 4. And then the next thing I need is looking up here. The velocity of Bill relative to John. Oh, I don't have that one. In fact, I've got the opposite of it. I've got John relative to Bill, not Bill relative to John. I got it backwards. It's just the opposite components. That direction is opposite to that. It's the opposite x component, the opposite y component, the opposite z component. The opposite sign for the I, the opposite sign for the j, the opposite sign for the k. So, oh, I can do this. I'm just going to turn around and go, oh, well, that's going to be minus 3, minus 2, minus 4. That thing tells me to add. So add, and that's going to be minus 5, minus 5, and 0. So my velocity of Lisa relative to John is equal to minus 5I minus 5J plus 0K. I still put the K down even though, you know, because it's the axis still exists. It's like just because the value is 0, the axis still exists. I think 0 is underrated as a digit. It's like, it's just as valid as 7, but people tend to just ignore it if it's a 0. And that is meters per second. Isn't that nice? So this is a really quite involved problem when you think about it. You've done a 3-dimensional relative motion problem, and it falls out. It falls out because it's, again, it's the layout and the keeping the logic, and that insight of the order of the letters really helps. Cool. There was something, a little alarm bells going off that I wanted to tell you, and I cannot remember what it was. There was a little alarm bell as I was doing it that was like, don't forget to tell them about this. And I've forgotten to tell you about it, so it'll probably come back in a minute. Okay, cool. So there we have it. So nice little 2-dimensional stuff. Let's stop it there.